Sure.
Yeah.
Welcome everybody to today's event. This is with Vinay, the Udemy instructor. And our next event is February 26th with Dr. Kamal Chowdhury and March 5th with Dr. Rasa Montasa. And the next one is March 12th with George Zeppelin. Another one is March 26th with Saki. And thank you for our sponsor for the partnership, Quantum AI Foundation, organized by Power Agora, Quantum Computing and Data Science in Toronto, Zeng for Mecca, OrionX.net, Association Quantum, Cambridge Quantum, Q Egypt, Q Mexico. And let's begin our event. Let me stop the sharing.
Thank you, Helen, and welcome everyone. I'm Virendra Galotra, and quantum has been my passion after AI and machine learning, where I have my research and, of course, pretty diversified areas which I have been dwelling into as part of my career and life, starting from databases to AI machine learning to databases and, of course, performance and architecture, and into cloud and situations where you are moving customers to cloud for our respective companies. And of course, I'm a global startup ambassador also. If you have any interest in joining a startup ecosystem for companies with Oracle, and I can definitely sign you up there as well. And of course, coming to today's topic, we have a very, I would say, learned, my friend Vinay Phadnis in the area, who is going to basically bridge us between AI, ML, and essentially focusing on genetic optimization acceleration using a quantum annealer. And basically, today he aims at providing a very basic understanding of how genetic algorithms work and solving simple logic problems. So he'll be talking about Turing completeness of machines and things like that. So gear up, fasten your seat belts, because it's going to be very, very technical. And Vinay has done the favor of sharing these sessions earlier also with us. So definitely it's going to be a good, solid technical delivery here. So over to you, Vinay. Introduce yourself. Feel free to give more, and after that, absolutely dive into the topic straight now. All yours.
Hi everyone. Thank you so much, Virendra. Thank you so much, Helen, Dave, for organizing this. So, yep, I got started in the quantum field a long time back through quantum mechanics and then quantum computing. From there, I created some courses on Udemy, and now I currently own a company in India, and we do quantum consultation to build programs on quantum computer. Then we focus on building custom solutions for companies and to build quantum security systems, quantum randomness, algorithms, and all those good things. So the journey has been full of ups and downs because quantum is difficult to get started. But ultimately, as you get the hang of it, you understand that there is no domain which is as interesting as quantum algorithms and which has an equal potential to actually create a big dent in the world of computing. So with that excitement, let's get started. Just one addition, I've recently recovered from COVID, and that's why I have a little bit of cough. So I will just take it a little bit slow. So just bear with me for that. So coming back to today's topic, we have quantum genetic algorithms. So let me first talk about what is it something that we should not be expecting today. So this is definitely not going to be a biology talk. This is going to be something which revolves around data optimization, machine learning, and exactly what are genetic algorithms, how can we take inspiration from nature, how do we learn from it, how do we put that in a more logical setting. And once all of that is done, we'll understand why that is something which was not used in a classical programming environment. and after quantum computers, what exactly has changed, and why are genetic algorithms actually making a big comeback in a way which no one can anticipate. Yeah. So to begin with, today we'll just cover these topics where we'll talk about what are the basics of genetic algorithms, then what are the steps required to simulate natural selection on a computer. We'll get into exactly how it's done, what are the different logical steps in it. Then we'll get into the problems with genetic algorithm and why has it exactly not seen its true potential. Then we'll see how a quantum computer is used to solve each and every one of those problems. And finally, if time permits, we'll definitely see a quick demo of quantum supremacy system, which is like a D-wave system. So, yep, to begin with, what is the buzz all about? Like exactly what are we talking about when we mention genetic algorithms? So at a very broad level, when we solve undeterministic problems, so by undeterministic, I mean when you get started with the problem, you don't know the exact solution. So these type of problems are called meta heuristics. So the approach which you take to solve these problems is an iterative approach. Like slowly you go closer to the solution. So something you can think of is a self-driving car. So if you're actually looking at a Tesla, then initially it was not very good at self-driving. But as the days went by, as more and more people started using self-driving on the roads, it got a lot of data. From this data, it was able to generate insights. It was able to train its neural network so that the next time when it sees a similar object on the road, it knows how to behave. So this is an example of a meta-heuristic problem where the solution is not known at the first day itself. It is generated through insights which are gathered through data. So in this, there are multiple different types of meta-heuristic approaches. So a very common one which is used nowadays is called a single solution based meta-heuristics. So these are all our neural networks, and this is exactly, it comes under the category of single solution because you just build one neural network and then you train the neural network as and when you get more data. Then there is another type of meta heuristics which is called population based meta heuristics. So here we plan to take help of nature, where we look at its own algorithm, like the survival of the fittest, which is nature's own evolutionary algorithm. And the loss function here is having a long life. So if you live longer, that means you did well in life, in short. So keeping that same principle ahead, we'll be looking at some of these problems and just to understand exactly where do genetic algorithms come in a broader sense of different problem solving algorithms.
So just to make one comment here, I'm deliberately taking that to give you multiple breaks in between, as you said, and hope that you recover very quick, Vinay. So from that angle, as you mentioned, a very good example for Tesla for our listeners and attendees. So the biggest IP value and the reason Tesla is ahead and with such a big market cap, even in spite of the reason that stock has been not doing so well in the last week or so, is that they have been ahead. And as when I explained, the data which they have captured, that is their biggest strength right now. And the way they have been ahead, software is of course one piece of the solution, but the biggest piece is the data and the mileage which they have captured through all these cars and their own capturing which they do, so that they can exactly identify the solution problems much faster and ahead of others. And that's where they have an edge over any other companies like Ford, GMCs, which are now jumping into free, and of course a lot of Chinese companies as well. So that's where their strength is mainly. And you might have all seen so many cars nowadays running on your local roads with big cameras on left, right, center, and all, and the multiple cameras. So that's where the fact lies. Go ahead, please, Vinay.
Perfect. Thank you so much, Virendra. And that is very rightly said. In the long run, data is the only valuable asset which we'll be looking at, because all of these algorithms to derive insights from data will be uh, so it will be so agnostic, so that actually the only real asset which makes sense is data. So yeah, coming back to genetic algorithms, let's look at a very simple example which is found in nature. So here we have an eagle, and eagles eat mice. So like considering like a couple centuries back, like let's say 500, 600 years back, the population of mice was fairly equal. Like we had a 50-50 distribution between gray and brown mice. But then what happened is these eagles started eating a lot of brown mice. And after, like, fast forward a couple of centuries, we have a lot of black mice present. So the population of mice uh, uh, had experienced a genetic drift, starting from a 50-50 population of black and brown mice to 100%, a near 100% population of black mice. So let's look at exactly what all steps are followed here, and exactly how did nature achieve this. So in the very first step, the DNA of the mice was 50-50, like 50% gray, 50% brown. Then we need to understand what is the goal in this scenario. So we are taking this experience from nature and we are transforming it into establishing some technical terms. So here, initially, the DNA of the system was 50% gray, 50% brown. We are ignoring all other factors, like how fast can the mice run, then how strong an individual mouse is. We are ignoring all the other factors. We are just looking at the color right now. So the goal in this scenario was survival. So if you look at this entire scenario where this eagle wants to eat these mice, that is called setting up the environment, where we have some predator. Based on that predator, we have a survival scenario. So the goal here, or the loss function here, is survival. So whoever dies first has a very high loss value. Then as we look at it, this environment is greatly unfavorable for brown mice, because that is something which the eagle can see from high up. So that is why, as the environment is unfavorable for brown mice, slowly their population decreased. Then as black mice started mating, started reproducing, slowly the number or the population of black mice increased a lot, and brown mice slowly decreased and they went towards extinction. So ultimately, the optimal solution for this problem was that the new DNA is 100% gray. So the initial condition was 50% gray, 50% brown. And then the final solution is one. Okay, so this is a very important learning experience from Mother Nature, because by simply pointing this scenario out, we can establish that we have an environment, we have a DNA through which organisms reproduce, through which new individuals are created. Then we have various generations of organization of organisms. Like initially we had a fair distribution, then slowly that started to drift away as more and more generations of mice actually passed by. So we have different generations, we have multiple individuals in a particular generation, and then finally we have the final solution, which is 100% gray. The DNA became 100% gray. So just looking at this same problem is simulated, the same thing concept is used to simulate logical problems where we have multiple steps. So whenever we want to define a logical problem, and by defining a problem, I mean we have a loss function, like something that we want to achieve. In this case, we wanted to achieve survival. But in the case of genetic algorithms, it can be anything. Like if you look at a self-driving car, the goal here will be minimum accidents and maximum time that the car can drive on its own without telling the driver to interrupt and take control of the car. So to do this, we have a couple of steps here. So the first part is encoding. So this refers to setting up the environment, which we did before, where we had that eagle, we had different color mice, we had land which was similar to gray color mice. So in the case of a self-driving car, we might be taking inputs of the road through cameras. Some self-driving cars have LiDAR. Some of them have motion detectors. Some of them have sensors to check the distance of the car next to them. So all of this data in real time is fed into the system, and this is called as encoding. After encoding is done, we go to the next step, which is selection. So consider that we are, so in reality, if we were to spin up 100 Teslas and let them go wild on the road, it would have been very difficult because we would be dealing with real life accidents. So instead, if you look at a software simulation of the same thing, what we do is we generate a map of New York City on a computer. We create 100 different cars and we let them run in the environment as they normally would. Then what we do is we do a selection process. So let's say we had 100 different cars. Then out of those, the top 50 cars could travel 100 miles without any accident. And then the remaining ones met with an accident less than 100 miles. So then what we do is we take the top 50 cars and then we do a crossover process. So crossover is like just taking two parents and generating a new offspring from it. So now our generation size is decreased from 100 cars initially. Now it is 50 cars because we decide to kill the lower performing 50 cars which met with accidents, which didn't perform very well. With the remaining 50 cars, we do a process of crossover where now we use the DNA of the parents and then we generate the next 50 cars. And if this process is repeated a multiple times, then slowly we have cars which perform better than the previous generation. And finally, we come up with a car which is having full self-driving features. Yeah. So if we look at it in a rough flow chart, then we initialize a population where we have 100 cars on a simulated road. Then we do the fitness function calculation. Like we calculate how far every car went without meeting an accident. Then we do crossover. So let's say out of the 100, we choose the top 50 cars. From those 50 cars, we do a crossover operation. After doing the crossover operation, we do mutation, where we add random operations in their DNA. So think of DNA in this case as something like which looks at the road and makes a decision whether to accelerate, whether to decelerate, whether to turn left, turn right. All of these decisions are taken by the core DNA. So then we add some mutation where it's like we add randomized operations on the DNA where suddenly we make some changes. Like if you see this, you turn right. Most of the times the car will crash, but sometimes we'll come up with a clever way of avoiding obstacles. Then from there, we again select the top 50 cars. We repeat the same process again and again until we have a car which satisfies our criteria. So to better explain this entire phenomena, I have a small video and we'll go through this video as well. I'll just see if I can play this. So is the audio, can you hear the audio from the video?
Hello, sorry, we cannot hear anything.
I think you may have to turn your audio on. Helen, is it control with you or they can do it? Hello? Am I not able to hear him or no one is able to hear him?
I don't think anybody's
I
able to
also
hear.
cannot hear him.
Okay. Then I guess I'll just speak up to it. That's fine. So see, guys,
you can share the
Yeah.
link with us. It is in YouTube, right? Yeah, it's not it.
I'll do it. I'll share the link. Okay, no worries. For now, we'll just go through the problem. That's fine. So the idea is we have a backpack, and in this backpack, we can just fit a very small number of items. So we're talking about headphones, we're talking about a notepad, we're talking about a laptop, we're talking about a coffee mug, water bottle, etc. So then what he does is he assigns a price in terms of how long is it taking to pack your bag for every different item. So, and after doing it, he assigns a code to every single item. Then he creates a fitness function for your bag, which corresponds with the weight and how effective your backpacking strategy is. Once this is done, he explains all of these concepts like genetic how do we come up with a more optimal. And once all of that is done, we come up with a good solution optimization. Okay, so let's go through some examples of what exactly is genetic optimization and how can we uh, improvise it further. So some examples are self-driving cars, where, as I explained previously, we have cars running on the road, and the goal over here is to run for a very long duration without meeting with an accident. Then the next application is drug discovery. So in order to understand this in detail, we need to look at how exactly does drug discovery work, where initially we just create random protein molecules which are known to tackle similar diseases. And after we have created these protein molecules, we test it on a sample virus. So let's say we are looking at an antidote for a particular virus. We create different protein molecules. We inject those molecules on an environment where the virus lives. And finally, once that is done, we try to see if the population of that virus is decreasing or not. Now, this is a very big trial and error type situation where we don't know exactly what will work. And that is why drug discovery is such an expensive process, where no one knows which direction should we go, what should we try out, exactly what should we do. So in that scenario, a lot of big companies are starting to use genetic optimization for drug discovery, where it's like they have a more directional effort as to exactly which protein molecules do we deal with, which two molecules do we perform a crossover so that the resultant protein molecule is better performing at the same task of annihilating that virus. Then we have different gaming bots. So you must have seen these examples where Google's AlphaFold performed very well in chess. It beat the world champion at Go. So all of these are simulation-based events where the entire game was taken, and then the bot was kept so that it can be running on that same game for at least a couple hundred iterations. And once it was done, it was very good at playing that game because it had the knowledge of a few million iterations. So this is also another way in which new genetic optimization is used to actually create bots that are sometimes better than humans, because for humans to go through 1,000 generations, it takes a lot of time. But doing the same thing programmatically is very fast. Then the next application is business process, where we look at various different ways in which a particular deal can be made. So let's say if there is an optimal price where the deal should be made, then we look at all of the extreme ends of the same scenario, and then different genetic optimization individuals are created. And then through the process of genetic optimization, we come up with an optimal point in business process optimization where we can come up with a deal which is not harmful for either of the parties. Then we have nuclear fusion, efficient solar power. Both of these problems revolve around around how to structure a silicon crystal in the correct way so that we absorb maximum of the input energy. And then finally, we have brute force gradient descent, which is considered the state of the art right now, because this is a particular algorithm where we actually use genetic optimization to make neural networks perform better. So clearly, genetic optimization has different uses, but at the same time, it has a lot of problems inherently with it. So the very first problem is that directionality. Like, just think of the same scenario where we have the virtual map of New York City and we have 100 different cars left on that environment in a random way. Now, the problem is we are wasting a lot of compute resources on cars that are not actually performing well. So, in this way, there is no directionality to that effort where multiple individuals are free to do whatever they want. And finally, we have large population setups that are required. Like, for example, if you just looked at the compute requirement of setting up a virtual map of New York City and then having like at least 1,000 to 10,000 cars running in it simultaneously, that itself is a very big computing feat. And then finally, as that is done, we still need to perform this task through a lot of generations. And the problem is these generations compulsory have to come after the previous generation. So these generations come in a serial way. So this is something which cannot be parallelized on a GPU. So the biggest reason why genetic optimization algorithms didn't reach the mainstream is because you cannot use a GPU to accelerate these problems further. So that is why modern algorithms like gradient descent took steam, because that is something which is very efficiently solvable on GPUs. And nowadays, if you run any machine learning algorithm, you know that it all boils down to how much GPU compute do you have. So the more GPU compute you have, the faster you can come up with ML results. And then finally, there is no guarantee of improvement, because even in nature, we see in the process of natural selection, a lot of species go extinct. And this is because they still cannot maximize on the goal of survival. So similarly, whenever you run this in a logical problem, then also you're not sure that you will actually converge on a particular solution. Sometimes you might just be running generations after generations of simulation, and it might not converge on anything. Then finally, there is this problem of genetic mutation, where we need to perform random operations in the DNA of every individual, which makes it further difficult because true random numbers is something which is very difficult to generate on a classical computer. And then finally, the biggest problem of genetic optimization is that we can get blocked in a local minimum. So if you are looking at a very big problem, like let's say the same thing, if let's consider the map of New York City, then we can come up with a solution where a car just joins on the freeway and goes for miles and miles together without facing any challenge, because it's a straight patch of road. It doesn't come across signals, it doesn't come across stop signs, it doesn't come across different cars which are traveling in let's say a perpendicular direction, it doesn't come across any intersections. So in this way, if the car just learns to travel correctly on a freeway or a highway, then we have reached a local minimum, because then that doesn't solve the problem of full self-driving, where the car doesn't learn to drive by itself, but still it knows how to speed on a straight road.
Yeah,
So
I think that's a great segue here, and I'll take a small interruption for you here with a question. When in terms of, since we are talking population here and we are touching on that area, a question is, can you also touch upon how in reinforcement learning model go and population-based optimization do, right? And is there any parallel between genetic algorithm and deep reinforcement learning models? So we'll break the question into two. First would be, you have addressed in some form or the other, but if you want to still touch upon that, how reinforcement learning model go and that does population-based optimization.
definitely. So in the case of reinforcement learning, it so there is a fundamental difference here where in genetic optimization, we talk about a large number of individuals doing the same task and hoping that they'll come up with a good solution. But in the case of reinforcement learning, what we look at is we look at just one individual and all of the actions that were performed till that car crashed. So we look at all of the turns, we look at all of the times where the car accelerated, where the car decelerated, and we treat every one of these as an action. And then we try to determine which action actually resulted in the car crash. And the job of reinforcement learning is to go back and track and make changes in these events so that ultimately it comes up with an algorithm which is more fine-tuned towards that particular environment. So, Virendra, coming to your second question,
Yeah.
the main point of difference here is in genetic optimization, we try to have something like a swarm-based intelligence where we use the power of multiple individuals doing the same thing. But in the case of reinforcement learning, we just use one individual and we try to train this individual to become a superhuman kind of environment.
Yeah, it's just like focus versus a mass population.
Yep, exactly.
Yeah, thank you. I think, in terms of a small follow-up, how can we better neural nets using genetic algorithms?
So a very good point here. So a lot of neural nets are actually being accelerated through genetic optimization where so right now what happens is every neural network has a certain number of weights and biases. Ultimately, a neural network is a collective representation of weights and biases, which are like numbers. So if you take these numbers and if you serialize them in a big array, this is exactly like a DNA strand. So it's like a big DNA strand. And what we do is we perform genetic optimization on top of it. And this DNA strand can further be improved to create better neural networks. So right now, the way in which weights and biases are tweaked is through a process called gradient descent. But instead of gradient descent, what some people are speculating is that if we use genetic optimization to just tweak the weights and biases, because ultimately it can be represented as a DNA string, then we can use a quantum computer to efficiently solve the problem of training neural networks, which is considered to be a very hard problem to be solved on a quantum computer.
Thank you. I think just to add one last comment for that, it's basically the evolution theory also comes in here, like every next generation is better because it's already inherited the genetics and then it's improving on the basis of experience, on the basis of interactions and environment settings and everything around further. And no one would challenge me on the statement if I close with that and let Vinay go ahead that your kids are smarter than you. Definitely. All our kids are smarter than us. That is a very natural way of progression. Over to you, Vinay, again.
Okay. Thank you so much, Virendra. That was a very good comment. And precisely, if I were to sum up genetic algorithms in one line, it ultimately means that our kids are smarter than us. And ultimately, we go on making kids till we reach a generation which is ultimately very smart.
Yeah, imagine nowadays when we see kids, and I'm slow, a little bit going off tangent here, but it's very relevant comment and everybody would correlate again to that. We were not born with iPhones in hand. They are with iPhones and they on their own learn and they operate better all even these simple iPhones against us. They were not taught any AI, which we were taught, and now we are trying to perfect that. 20 years back, AI was not there. 5 years later, quantum will be again in the mainstream. And I keep saying that in every single session we moderate and we discuss that AI took 20 years, whatever time it took to come to this level of adoption and everything, because of the challenges we had on hardware, software, and as Vinay explained, that now we need GPUs and TPUs and everything to go better with that crunching power and computing power. And yes, he will be talking further in the session also in terms of where the hardships are at as of now with quantum computer, and where right now we are doing all these simulations using AI ML and going to quantum computing. So this is a gap which I feel, and I think later after the session we could talk more on that in terms of this main content when it is over and we have time left, is that would it take that much? Would it take lesser? Or you think we are already moving faster than we thought? And with all the Fed and all the funding which is coming through for quantum computing and everything, which is already staged, again, going back to our environment settings, I'm very sure things will happen much faster. But all we have to take care is we keep it on the positive side of the things and don't let it drag to the negative sides. But reality of the human race is we have both sides of the story. But with that, back to you, Vinay.
Super, super. Thanks for that. And Virendra, I'll take a segue from that and come back to genetic optimization. So, guys, let's summarize what we did until now. We just understood what is meant by genetic optimization, what steps involve genetic optimization, and then we kind of saw some examples of where exactly is genetic algorithm used, are genetic algorithms used. And finally, we saw some problems due to which this very efficient toolkit was kind of staged and no one really saw a very practical use for it, is because uh, it requires a crazy amount of computation. But at the same time, somewhere we know that this is the ultimate toolkit which is required to come to a solution, because that is how we have been surviving for millions of years. Because it is in a way mimicking nature, and nature is the longest surviving entity, as I would say. So let's look at what can we do to get to get genetic algorithms back to the mainstream. So as quantum computers are getting more and more popular, we are actually seeing a lot of very interesting applications. So the very first application with a quantum computer is how do you generate truly random numbers? So if you look at it, for a classical computer to generate so truly random numbers, so fundamentally, let's look at how a classical computer functions. So these are Turing complete devices. So by Turing complete, I mean that we can simulate a problem on these devices, and it can take a certain number of steps to solve that problem. So ultimately, if you look at a classical computer, it is a very deterministic system. So each and every operation is encoded, each and every data bit is encoded. And finally, because of that, what happens is generating random numbers become very difficult on a quantum computer, on a classical computer. So that is why even in the case of genetic mutation, where a large number of truly random numbers are required in order to escape this problem of converging in a local minimum and instead going on a global minimum scale, for that we can leverage quantum computer, where we have something called quantum noise generation. So through this algorithm of quantum noise generation, where we take a very simple quantum stage, we prepare a number of states on whatever number of qubits we get. After these, after we have prepared quantum states, then we do measurement. After this measurement is done, we inject some raw noise. And after that is done through some post-processing steps, finally, we get a message that is truly random with reference to the initial states that were fed into the system. So with this, we can actually perform genetic mutation to a very good degree. So yeah, the next part is quantum sorting. So if you come back to the same problem of having a self-driving car in a big city, then one very important problem is that, let's say you are referring to 1,000 different car as individuals kept into that scenario in that simulation. Then the biggest problem is how do you sort them? Like exactly how do you classify which car performed better? How do you rank them based on their fitness score? So here the fitness is how far did the car travel without having any accidents. But then there are other constraints also, like did it overspeed? Did it perform a turn that was not legal? Did it use the wrong side for the entire time? Did it drive through grass, which is not correct, but still it avoided accidents? So these are a lot of ways in which we need to sort different individuals as well based on their performance. So this is a very interesting algorithm, or a very interesting pseudo code for quantum computers, and something called BOGO sort. So as you can look at it, it's also sometimes converted as a meme, where we have no sorting logic here, like absolutely none sorting logic. But what we do is, as a quantum computer, if the list is not sorted, shuffle the list. That's it. And we repeat this until the list is sorted. So isn't this crazy? If you think about this from a classical computer's perspective, you would call this programmer an idiot, because he is not converging on a solution. The list is not being sorted slowly. The list is not being like the there is nothing. How can we even define the time complexity here? It is crazy. So that is why if we were to look at this algorithm as a standalone program on a classical computer, this is crazy. But if you look at the same thing on a quantum computer, then this makes a lot of sense, because quantum computers are fundamentally non-deterministic systems. So remember the problems where I was talking about, it's not necessary that we might converge on a particular solution. This is exactly what same the BOGO sorting problem is, where if you run this through a classical computer, you might never come up with a sorted list. But in the case of quantum computers, through processes like quantum tunneling and quantum entanglement, this can be converted into a constraint satisfaction problem. And once that is done, you can actually solve, or you can actually sort this list based on just randomly shuffling this list again and again. So this is a very important way in which quantum computers can actually help you create a sorting algorithm by not writing any sorting logic, but by just randomly shuffling this list. And this is again very effective, because quantum computers can generate truly random numbers and not pseudo random numbers in the case of a classical computer. So ultimately, guys, let's again go through the steps where we'll look at genetic optimization again. So to start with, we initialize some population. Then we test every individual in this population. So it's like again running a car in a simulation environment. After this is done, we evaluate the fitness of every individual. So how far did the car travel? Was the driving ethical? Was the driving legal? Then was it risky? Then how do we rate it on a risk profile? Then finally, we set the best individual as the evolution goal. So we look at how well did the top individual perform. And based on that, we rate the entire generation. And the goal of the next generation is to perform as well as the previous generation, the top performer of the previous generation. Then we check if we have met the final condition or not. So in the case of self-driving cars, of course, there is no final condition, because even if the accuracy is 99.999%, that still means one person in 10,000 people driving this car is going to meet with an accident. Even if you improve the accuracy 100-fold, that still means one person in 100,000 self-driving incidences is going to meet with an accident.
And I will take a small break
Define
here
a
again.
condition where at
I mean,
least
when we have two questions, but definitely because we are going away from random number generation, so I thought we'll just take a small quick segue here for this question, which is pretty interesting. The question is basically, can we generate numbers randomly simply by measuring QU bits that have been put into 50-50 superposition?
Yep, that is the exact idea. So
Yeah.
the idea is, when you have a qubit, in a 50-50 super, exactly which state is it going to converge on. So by just keeping qubit in a 50-50 superposition and then measuring the state, then you have any one of 0 or 1. What you do is you repeat this process for multiple qubits until you have a certain number of bits, and those bits are combined 0, 1 bits to get a random number. So that is exactly what we are we are doing here. But the only challenge is sometimes having qubits on an exact superposition, like a 50-50 superposition, is very difficult, and sometimes it requires a lot of logical operations on these qubits. So that is why we inject random noise. Like even if we don't have 50-50, we have 40-60, and to offset it, we have another 60-40. Till the combination results in a random number.
Thank you. That explains it very well.
Yeah, perfect. Do we have any more questions?
No, this is
Can-
fine. And now only a query which just popped is, why are we repeating experiment if it is random?
Perfect. So yeah, this is actually a very good point. And the only reason why we repeat experiments on a quantum environment is because we cannot reach a noise resistant environment. So let me elaborate more on this. So when we define or when we create a quantum computer, in that case, whenever we add some states on the qubits, like we perform some logic gate operations, then the problem is this is in a completely noise resistant way. So that's what I meant by having by not being able to do a 50-50 uh, uh, state split exactly. And that is why we repeat it multiple times, so that even if there is any deterministic element, that is removed over the course of running this experiment multiple times.
That's correct. And just to give you another simile on the same example of running multiple times, and again, I take very simple example of something called law of averages also. And also when we take to any stock portfolio, for example, to maintain it optimally, perform it optimally, and hedge it from those situations, we try to take 30 stocks minimum in a portfolio. That is the magic number. So that when things go up and down, basically that random behavior and that movement of stocks in positive or negative direction, we try to come up with a stable portfolio. That's where, again, that kind of situation is a very simple layman example of what we just discussed in very technical terms with Vinay. Thank you, Vinay. Go ahead. Vinay, can you hear us?
Yep, I can hear you. Sorry, there was some. Okay, perfect. Now is my screen clear?
Yeah, we are good.
Perfect. So, yeah, let's just summarize the workflow till now. So ultimately, we were on this concept of having a final condition. So in some problems, defining this final condition is very difficult, but still we define a criteria where the solution is acceptable enough. So it's like, even if we say that one person in 1 billion people is going to meet with an accident, that is still a million times better than normal humans driving on the streets. So it can still be considered as an acceptable level solution.
Absolutely.
So,
And that's a
yep, finally,
interesting
once that
stage. Yeah. That's a
is
very
done.
interesting example. Thank you, Vinay. Keep going. I'll not interrupt you.
Okay. So, yeah, once that is done, we test every individual. So it's like we refer to. So it's like we refer to the progress made by every individual, and after the fitness score is generated, then here we do something like a quantum rotating door solution, where we update the population through a quantum process. So this basically this quantum rotating door algorithm is something which is a very complex algorithm and maybe not in the scope of today's discussion, but in a very simple way to explain this, it is more around generating random numbers, and through these random numbers we do quantum mutation, and once quantum mutation is done, that is used to generate a new population. So mutation is randomly changing the DNA somewhere in between. And once this is done, then we check if this is a disaster or not. So this is also a very good situation here where sometimes what happens is a generation turns out to be very bad, where none of the individuals in that generation are performing well. That is called as a disaster. If that is done, you just kill all of the population, you create a new generation again using random numbers. So here, this is where we start to appreciate the beauty of genetic algorithms. It is very difficult, or I would say impossible, to do this in the real life, where you can randomly start killing generations, you can create new generations, you can decide who is the best, you can rank people according to their performance. And finally, as this is done, we increase the time factor also to show that we are referring to newer generations. And guys, this is exactly how a quantum-based genetic algorithm works. So still, um, this is not a foolproof solution, and this is still something which is seeing extensive research done every day. But this is a very good problem, because if we are able to solve quantum genetic optimization, that means we are taking a very big leap forward in quantum machine learning, where instead of trying to simulate how neural networks work, so it's like neural networks work in a very classical computer way. If we want to simulate it on a quantum computer and just add an accelerator, that is not enough. We need something which is truly undeterministic, like a quantum computer. And I think genetic algorithms are a very good way to actually think about this type of solution, where we have an undeterministic approach towards solving a problem. So here again, the same thing. We are trying to come up with a sentence which is to be or not to be. And for this, it is again generating a random number of individuals. And this is just a good example how individuals are ranked. So if you look at it to the far left side, if you look at the top, then we have the sentence which is the farthest away from to be or not to be. If you look at the right hand side, we have sentences which are very close to be or not to be. So this is how we rank different individuals, and that is how we come up with an objective programming to solve these multiple problems. So yeah, I hope we were able to actually get a good rough understanding on how genetic algorithms work. Then how can we use quantum computers to accelerate each one of these processes? And once that is done, we can actually come up with, we can redefine the way quantum machine learning actually works. And I'm personally very interested to be working in the quantum genetic algorithm area. That is something which I'm doing for the past 1.5 years almost now. And this is a Udemy course which I had uploaded some time back. So if any one of you is interested to explore this topic further, to explore exactly how do we perform operations on the D-Wave quantum computer, or what are genetic algorithms, how do we do this programmatically, more than happy to give you guys a free access to this. And yep, that's pretty much it. That's all I had. I later on more than happy to get into details, because it will be too mathematical for a general audience, and I think so a lot of people will lose interest. So yep, that's pretty much it. I'll leave it here and maybe open the forum up to some questions. This is my number. I have my email ID, my LinkedIn, my Udemy profile. So feel free to reach out to me if in case you are interested in quantum computers. I am also working with the Unitary Fund. to create quantum computing applications. I'm working with their panel who specifically has access to giving grants to quantum computing projects. So if you're working on anything interesting, feel free to reach out to me. And I own a company called Atomic Loops, through which we do quantum computing consultations. And yep, definitely looking forward to talking with all of you. I'm a little sick this time, so had to keep it a little short, but more than happy to talk more in the question and answer session now.
Sure. When I will not keep you for long, I'll just keep you for two more questions today, considering you are sick. So we'll not extend this session and we'll come back to the same channel another time. But definitely thank you for sharing all these details and all the good work you're doing in the computing and especially quantum computing areas. And guys, let me tell you, Vinay has been very, very modest in terms of his presentation today. He is a hardcore AI, ML, and quantum guy. I have seen and I have worked with people before in this area. He's on the top of my list. So with that said, the simple question which people are asking at this stage, one of them is, now when we are basically repeating the experiment, if it is random, and where is that random noise coming from? The one not from superposition measurement. And that's what I believe you already answered, that we are introducing some noises also. That's one piece of the story. But to extend that piece further, are we using quantum computers here just for introducing noise or inbuilt noise in the system? And this is in the context of what you spoke, Vinay. That's why I'm just trying to give you verbatim that by the uncertainty in the quantum measurements. This could be a pretty useful process for training the machine. Comments on that?
Yeah. So a very good point, actually.
Yeah.
So actually, we are definitely using quantum computers for two different things here. The first thing is noise injection. So the most, let's look at it in this way. Let's think about it. So if you're looking at quantum random number generation, the easiest way to do this is do a 50-50 superposition, where we have a qubit, which is either 0 or 1. Now we measure this qubit and it can randomly collapse in 0 or 1. But in practice, what happens is this is never exactly a 50-50 superposition. Even if we use the state-of-the-art quantum computers, this always is a 40-60, 49-51, or a 20-80 type of superposition. So now, in order to overcome this, we also use quantum computers to measure noise. So this noise is the difference between two different qubit states. So let me elaborate more here. So considering we have two different qubits, and this only works when you have a non-perfect environment. So if you had a perfect environment like absolute zero, then complete superconducting state, both of these qubits will be in an absolutely equal state. But when you inject some noise in the system, which is usually the case in any quantum computer, like they all fight whether whose noise is the lowest, but no one claims to have zero noise because it is impossible considering the laws of physics. So what we do is, just because of these irregularities in the system, we just measure the difference between two qubit states, and that itself can give you random operations, because you have different noise levels affecting two different qubits. Again, they have their own superposition levels. When you combine both of these things, you get true random values. So I hope this answers your question. It is like, this is an inefficiency of the system, and that is why we have to resort to coming back to noise reading.
Right. And another follow-up question still about random numbers was, is it possible to use superposition to produce random numbers simultaneously?
So that's the thing. Now, I don't know what exactly do we mean by simultaneously. Do you mean generating two different numbers at the same time, I would say that is not needed. Just generate any one random number and you perform n number of mathematical operations on it, you get a different random number.
Correct.
So as long as we have the capacity to generate truly random numbers, it does not matter if we can do it simultaneously or not. As long as the start is random, you can convert it to as many numbers as you want.
Correct. And just to add that, normally speaking, we always, that's why I use the terminology pseudo-random, because they always, if you go through any cycle, any machine, any random number generation, of course, unless you are tampering in between and adding any noise to change the cycle or the periodicity, you can exactly create starting from 1 to, for example, and if you have taken a cycle of 50 random number generation, they will start repeating after 50 back to the same numbers. So that's the property, that's how they behave. So from that angle, that's why I wanted to bring this up. Yes, normally when it is random means you want to generate one, and as Vinay said rightly, it's like the channel. If you have one channel, that's how you want to generate that, unless there is a different kind of connotation here which you had in mind, Saurabh, in terms of asking that question. If you are trying to use two separate outputs from the same, or two different inputs and two different outputs for some different kind of application you had in mind for that question. But feel free, if you can unmute your phone or add again to the chat if that did not answer your question or you have some more follow-up question. So silence on both ends means kind of a no here. So I think this is very interesting and this is very thought-provoking in terms of what Vinay discussed in terms of genetic algorithms. And if you look back at nature, a few comments here, very, very interesting comments. And as Vinay was explaining that we are taking one person and we are making it superhuman. Doesn't nature do it that way? Nature does it that way only. If you look at the herd, lions, they have one lion leading the herd. You look at monkeys herd, they have one strongest monkey who has to fight through the herd. And during one particular season or whatever couple of seasons, he has to remain strongest to impregnate all the female monkeys. This is all research on geography channel. You can see that. And the reason of the nature is very simple: to take the best and the strongest and survival of the fittest. All those factors play in from those genetic, I would say, algorithms, which nature deploys on its own. Someone might have given thought to that, someone not. But those things did come to my mind as we were talking through this algorithm here also, because everything we have taken in terms of technical or into the field or anywhere, it has very good symbol in terms of the nature, where nature has been through these zillions of years and how they have been coming to the next generation and producing every time the smarter and better, smarter generation to survive. And those who could not, even the bigger dinosaurs, they were extinct, they've gone extinct. So those are like very interesting examples if you think carefully in unison with the technicals here. And I'm sure in any follow-up session, we'll have Vinay provide some more details in that more technical fashion, but he has shared all his Udemy and this course and everything. If you definitely want to leverage more of that, you can sign up for those. And I believe as Vinay showed some pricing also on that, they are very cheap programs and very, very affordable programs which you can leverage.
I'll interrupt you, Virendra here. If anyone wants to join it, just drop an email. I'll give you a link where you can enroll for free.
Awesome.
So absolutely no worries there.
That is the advantage of this forum. Thank you, Vinay. But in any case, like they are very, very affordable, and I want people to use both the channels simultaneously. Of course, free is fine. If you are offering that, very welcome. And guys, absolutely take advantage of that. And as I mentioned earlier, in terms of the Oracle startup program, which if you are having any startup companies through that program, I can introduce you to 400 different Oracle startups where you can go, you can exchange products. You can exchange what they are doing, what you are doing, go to market, and the product knowledge and product help and engineering and development interventions if you need any. And especially if you are a company which is platform agnostic and you want to have Oracle as one of the platform also for doing whatever you are doing, you can always leverage that program, and feel free to reach me for that. And I can connect you, and you don't have to worry if I'm in US, you are anywhere else in Canada or India or anywhere, absolutely in the right time zone, in the right fashion. We can get you connected to the local resources there who can help you exactly. So that's not, geography is not a boundary nowadays, as exactly we all know. Of course, Vinay is really burning his night oil today at, I would say 12:36 now for him in the night. It's AM, all this categorically speaking. If we have nothing more for Vinay, we should let Vinay go, since he's been gracious enough to keep up the appointment in spite of being down with COVID recently. So thank you, and thanks a ton, Vinay, for this wonderful lecture today. And any other comments and questions, you are welcome to send us. Even if Vinay today can't answer, we can make sure you can reach out, and you can send him directly also. Send it through this forum and we'll get you the answers if you have any questions. With that, let me hand it back and open the forum to
Virendra, just one thing. I think so we can spend just 10-15 more minutes if it's fine with everyone. We can answer
as long as you are there.
because,
As long as
I'm all in.
Yeah,
because there are some very interesting questions here which can shed a lot of light on what we just discussed.
Yeah, so let me see if we missed any questions. Guys, if I missed any, of course, we'll have the recording of this talk. Helen, can you speak up to the recording and where they can find recording of this and the previous sessions also after any questions which are left? So I think there are a couple of questions. I think I'm just scrolling down. So why don't we go through that? Let me pick that up further also. For classical computers, we use NP hardness to generate random numbers. Is that correct? Rapid fire, it is Vinay now. It seems like
So a quick answer, it's correct and not correct also, because I've seen a couple of Python libraries and all they do is they query the AccuWeather API and they just check the weather at a very distant location on Earth, and they use this weather data to generate random numbers. So anything is used to generate random numbers as long as it is difficult to trace back.
Thank you. And the next is coming to GA on quantum. Are you modeling them as QUBO or hybrid gate circuits?
This is a very good question. So the point here is, if we look at QUBO or quadratic unconstrained binary optimization, the whole point is this is used for deterministic problems where we know that we have a certain set of constraints. Like a very good example is a constraint satisfaction problem, where the rules are clearly defined and the end state is correctly defined. But in the case of genetic optimization, neither of that is clearly defined. So that is where we use hybrid gate circuits. And again, it's not like it's entirely solvable on a quantum computer. Parts of it are being researched and slowly moved on quantum so that the classical intervention can be minimized. And ultimately, we can solve the entire thing on a quantum hardware. So the answer is we use hybrid gate circuits.
Thank you. And I think that's a very interesting comment where I would like to add something. Nature, biology gets caught in local optima. Yes, nature, biology, and all of us in some way or the other, we get caught in that local optima where if we are not putting ourselves to more challenges, as Vin explained in a very good way in that lecture, New York and straight roads and no kind of hurdles, and there are minimal accidents. But the moment that chaos is added, bias is added, all those factors are added, and that randomness is added, things are different. People are caught in that. I mean, I was refraining, and I did refrain in during the lecture and stopped my comment, which I'm finally coming to at. It's a very interesting stat to look at. A stat in terms of how many accidents have been happening generally, and overall how many accidents have been caused by self-driving electric cars even until now. We do see sometimes some resistance, whatever the reasons are. We are not getting into that political discussion there, but I'm very sure, and anybody should disagree with me, still the number of accidents caused by any electric cars or all electric cars taken together will be way, way less than anyone. Because when it comes to human driving also, we are somewhere caught in the local optima always. And I know of some friends, and especially for people in Canada and US would correlate to that example. Some friend, someone or the other, whom I have seen driving for years, not getting into the freeway because they do not want to cope up with that speed in the freeway. And obviously that randomness and those uncertainties which can pop up at a higher speed, and they love to travel on lower speed zones and lanes and those areas. And some of them are very interesting. I've seen a friend driving not on freeway for the last 15 years without getting into freeway, managing her means, and my friend's wife. So I'm sure everybody would pick up some example like that from other aspects of life as well. And that's why sometimes when even people are trying to change profession or talking of the profession, they always say, hey, if you are good here, fine. If you're not happy here and you want to step out of your comfort zone, that's where now you have to take that challenge, step out of here and do something different, something new. And there is a risk to fail there as well. Isn't that something like getting caught in your local optima, where you are absolutely happy where you are doing whatever minimal or maximum you are doing, and you don't want to disturb those minimas and maximas, and you want to operate within that? Any comments, anyone? Vinay, feel free to add here something.
No, very, very nicely explained. I love the way you talk about global and local minimum. Very, very nicely said.
All right, thank you. Next, go to our next question. I think, Vinay, this is for you. Definitely you want to, if you missed or I missed something in terms of your certificate trainings, you want to receive lecture documents and file video meeting, of course, and some certificates. So I believe even when you are telling people to use the free link, they will be able to procure the completion certificate for the training program, right?
Yep, that's correct. So as long as the instructor gives a free link, it's still eligible for a certificate. So that should not be a problem.
Perfect. Thank you. I think that's very good for our friend here who's looking for Soravit from RAC. I hope I didn't butcher your name. Apologies for that in case I did. And I think apart from that, anything I missed? Helen, can we open the mic for people? If they have any question, they can ask direct also. I have exhausted, I believe, all the comments and questions on the chat also. I'm sorry. Earlier, I think my thing didn't pick up all the stuff and we had missed few, but I believe now I have picked up everything. Anything else? Someone was trying to speak, sorry.
I have one about the meta-heuristic.
Go ahead, please.
At the very beginning, you talked about meta-heuristic.
Yeah.
And question is this analog to unsupervised learning?
So a very good point here. So ultimately, we are only concerned with a particular loss function being met. So I would call this in the category of semi-supervised learning.
The other question is the number of layers in deep learning reminds me of this number of generations in your GA. Is this correct?
Not really. So if you were to compare it, like have an apples to apples comparison, the number of generations in genetic optimization will be equal to the number of epochs or the number of training cycles which we get in the neural network. And the number of layers in the neural network correspond with the number of individuals in every generation.
But the number of layers allows for correction or mutation between generations. Like
Sorry,
if
I
I
didn't
go
get
from
it.
layer to layer, I project whatever I found in layer n on layer n+1. So during that projection, I may either condense the information, make it more compact, or lose some information that is irrelevant or unfit in terms of Darwin. And therefore, I progress to the optimal convergence, to the close to the ground truth, which is unknown when I'm starting.
Yeah. So, okay, but do you want my comments on this? So, I would say, see, the thing is, this is the difference between neural networks, which come under a different category of heuristic solutions, which is like a single solution based heuristics, where we define the layers, we define the number of layers, the number of neurons, we define the architecture of the ML model. Once that is done, the only variable is the data and how much training we put in. But in the case of genetic optimization, along with this, the population, the number of generations, all of these are all, are also variables. So in that way, it's more like this is a more abstract solution where we cannot really compare the learnings which are transferred from layer to layer in a neural network. There is nothing like that happening in case of genetic algorithms because no individual is learning from one another. It's like it's a swarm based intelligence approach.
Okay, there is one more thing about those layers and trying to find analogy to the GA, and this would be the width and the height of every layer matters a lot. Like the width and the height of a matrix also matters for the analysis. So the analogy would be in the generation to generation, what kind of endurance or properties of every individual generation can be considered in the acceleration process that you alluded to.
Very good point. So here, in case of genetic optimization, what we do is we increase the number of individuals, and that improves the probability of actually coming to a solution. So it's like if you increase the size of the neural network, it requires more compute power. Similarly, if you increase the number of individuals in every generation, it also increases the compute power. So it's like the number of individuals, I would say.
Yeah, that always helps, of course.
Yeah, it's the same thing as when you use any pre-trained algorithms also in neural networks to come up for a faster solution and faster converging. Those are the kind of similar examples.
When I go to your favorite example, which is driving, self-driving,
Yep.
how about several or many self-driving cars on the road? And I go with my Mercedes, the conventional Mercedes, and how do I find my way there? Namely, I'm not looking at one self-driving car. I'm looking at a group of them.
Correct.
And then let's call them the slow or conventional drivers have to manage or survive.
Mm-hmm.
So life can get very interesting here.
And that's exactly the reason I loved your simile here and your comment here, and I would like to extend that further in that direction, that I am looking for a day which will not come very soon. Of course, it'll take time, but at least where you have more electric and self-driving cars, because then, and also somewhere when you have any controlled environment, let's take that example in a very controlled environment. And in that controlled environment, if you, let's say, take for an assumption here, everything is self-driven, everything is automated. That is a better survivability example for those objects operating in that controlled environment versus the one where we have more randomness, where we have conventional drivers, slow drivers, fast drivers, and electric drivers. That's where uncertainty is more. And that's where I would say, I have some friends who said, we have not gone for fully automated solution in electric cars because still they do not feel comfortable in relinquishing that control completely to the equipment or car versus driving themselves and yet having the electric features of the car so that they are environmental friendly also, and they can control all the uncertainties which are happening around. Because no matter now, let's go to the typical neural network example we were talking also. In the neural network also, the efficiency and the predictions and everything, how close we go to the final, I would say top percent, which is something is always missing. And that's what exactly Vinay also mentioned in his example also earlier while he was talking, that we can change the variables, we can enhance the predictions or the final outcomes and everything. But perfection is something, I would say, it's a still far-fetched game in all these examples we talk. But of course, there are some things where we have gone very good. For example, by virtue of a repeated data and a typically black and white mice example. I mean, that's where nature has evolved on our way. But computer vision, for example, in that arena has done much more better, but still there are a lot of challenges there. Because when it comes to the image recognition, it has gone way far superior as compared to years ago. And that's why when people have taken the courage to support all these autonomous self-driving cars even on the road, at least if within that discipline, if let's say you have 4 lanes, or if we say, for example, if in California or all over US and Canada, we have fast lanes. So if we decide to have autonomous lanes also tomorrow, I'm just going, guys, speculating there. But they say somebody has to take the dream and someday some will make it happen. So from that angle, that dream may happen also, that if initially you will have to keep it in a controlled environment. I'm going back to basically that controlled environment for fast lane or slower lanes, and controlled environment for example, autonomous cars, because that's where those cars indirectly or directly will be talking to each other in that autonomous zone, and we'll have more safety there, and yet we'll be able to reduce the accidents, even whatever percent we are seeing as compared to others. So that's where I believe in terms of those things we are headed. How will we take it? Will we see it in our lifetime, or it'll take another lifetime? I do not know. Those are absolutely open answers, right?
This is like technology versus alcohol.
Yes.
On the road.
It is.
Can I make another comment, like, again, using your example of the stock market?
Mm-hmm.
Because the more volatility, the traders are happier.
Yes.
But the slow learning, these people who just do the trend is your friend, but the trend is getting mixed up on you.
Correct.
Because of the volatility, which analogously could be noise or even quantum noise.
It is. It is noise, it is sentiment, it's all those things taken together. You are absolutely spot on in your comment. Absolutely. And exactly when you say, if we were to put a Grand Prix driver on the regular roads in the traffic conditions or peak area time of driving, are they going to really love it? No, they're going to hate it, right? And I remember, and I'm giving you example way back from years ago when bigger cars and faster cars were introduced in India, also 25, 27 years ago. A cousin of mine got a brand new car and traffic was already bursting through the seams those years also. Now it's anyway the worst traffic. We all know it. Nothing good or bad about that statement, but that is the reality and the fact. So I teased my cousin. I said, you got the car. When do you drive in the bigger final gear? And he said, I go at 2:30 a.m. in the morning to put the car in that gear. That's the only time I can put the car in that gear.
Yeah, it's almost like if somebody is hard at hearing, if you take them to a very modern teenager discotheque, they don't like it.
Yeah.
They cannot like it.
They can't. It's like setup of environment, which was one of the factors, very first factors which Vinay listed on his slide, right? So that those parameters will not match for those people.
But also the
what we-
self-driving car may be confused by the slow driver.
True.
That's
Yes.
why in Germany, the autobahns, you are not allowed
Yep.
to drive below certain speed.
You get a ticket. Yes. Very true.
Yeah.
Great. I think that's been very wonderful participation, lively participation. Any other comments? And whenever is your steam going off, let us know when you want to take off. We can absolutely wrap up the session. I see Hamel popping up there also on the screen as well. And Helen, do share with the folks how you want to share the recording of this session.
Will be on Orion X start at YouTube. And actually, there's a question. Are we replacing number of individual link point of each neural layer by only neural layer? Means we are looking the resolution by only layers rather than each individual point of single layers.
So a very good question, Dave. So see, the point is we cannot really compare genetic algorithms with neural networks. Okay, it is like consider any different machine learning algorithm like linear regression, decision trees, very simple ML algorithms. We cannot compare these with neural networks. So if you look at genetic optimization, it is a way to optimize your program further to reach the solution in a better way, in a less brute force way. So we cannot really pinpoint this in such a way that are we replacing layers with generations? Are we replacing number of neurons with number of individuals? It's not like that. Genetic algorithms and neural networks a lot of time work together in order to perform, in order to come up with a solution which is converging better and also uses the strengths of neural networks. So it is more, think of it like an accelerator on top of your software.
Thank you. Any other questions, any other comments, guys? If it's heading for a silence, then I believe you can take the final comments. Helen, provide the details for recording and we can adjourn the session unless you have anything else to add, Vinay.
No, that's pretty much it. And Virendra, thank you so much for being this very lively moderator and helping me out throughout the session. I really appreciate your inputs here.
Thank you very much. It's been a pleasure to be part of these discussions. It's a learning for everyone.
Likewise.
Thank you all, Vinay, and get well soon. We all wish you a good and come back again. And Virendra also. Helen, you can give us the website also again for the our coming up, next Tuesday's session. Okay. Thank you.
Thank you, everyone.